Good. Okay. I did my lab on yo-yos. Yeah. So the purpose, I really wanted to determine how when I added mass, like a circular mass to the side of the yo-yo in this cup, how, or if at all, it would affect the elapsed spin time and, let's see, like the period, like how fast it was spinning. I hypothesized that as I added mass to the yo-yo, it would spin slower, but the amount of time that it would spin in total before it stopped would remain constant. So just everything I used, I had this yo-yo. I needed circular masses, masking tape, a ruler which was just used in my setup for hanging it, a camera, and a computer with Logger Pro and a stopwatch. Oh shoot. Well, this is just a video of it, like my setup, how it worked. It was basically attached to a ruler on the side of a desk. I'd wind it up and release it until it hit the bottom. Procedure, yeah, it was pretty much shown in the video, but just wind it up and drop it. And so I would record the entirety of the fall, so from top to bottom, and I'd also measure the amount of time it spun on the bottom of the string before it started to stop spinning. Then after one of those, I would put one circular mass in here and then secure it with masking tape. And then I just keep doing that, and I had 10 masses, so I did 6 trials in total. 5 with mass and then 1 as control. And then I used Logger Pro video analysis to determine some of the experimental values. Okay, background, just a few equations. I think one of the most important parts of this, just for the simplicity of my equations and calculations, I'd assume that the yo-yo was made up of 2 discs. So these, instead of being like really oddly shaped, I just assumed that they were cylinders, and that the bearing is not spinning, which it's not. Just to help with calculations that use moment of inertia. So I could just use 1/2 mr squared instead of some weird summation of all the particles. Okay, so when I did video analysis, basically what I did is I drew a point on the masking tape while it was spinning. And so this, while it was spinning, I could track the point on the yo-yo. And then since I knew its radius, which I measured, I could calculate how fast or how long it was taking to make one full rotation and like the distance that that point was traveling. So I could really easily calculate what was I gonna say? Oh, tangential velocity. So this looks like this because I was assuming that video analysis on Logger Pro would let me kind of analyze things from a rotational point of view, but it didn't. It only let me do things in like a standard XY plane. So I had to analyze the position of the point on the yo-yo in the x coordinate. So if you imagine the origin being in the center of the yo-yo here, if I graphed a position on the rim of the yo-yo as a function of time, as it was spinning, the position on the x-axis would increase and decrease just like it would. And so basically, when it was at the very top, the position on the x-axis was 0, and when it was over here, the position on the x-axis was the radius, which is kind of like the amplitude of each wave. Here's some of the data I took. A lot of it was calculated. So, yeah, I think, yeah, graphs. So this is like, as you can tell, really linear, but it's only because this is made up of columns that were calculated, since the only experimental value I could really have was the position that was shown on, or like in the video analysis graph. So, sorry, I'm getting a little confused with my own data. This is really linear because it's made up of calculated values, but if I could measure the velocity with like a photogate or something like that, then it would have a lot more value. And the slope, I think, would be equal to either the circumference or the angular displacement. I forgot which one. Okay, so before I talk about my error, I wanted to explain something. I don't have too much time, so I'm going to try and do it really quickly. Let's see. Okay, so if you imagine two yo-yos, one that has...
Can you do it on the smartboard so that the video can see?
You can see.
Use the marker.
Will it work? Or will it start clicking?
Yeah, it'll work.
Okay. If you imagine two yo-yos... So I'm going to have to stand in the middle of it for a second. One that is twice as massive as the other. They have a downward force of the weight. And the torque that is causing it to rotate is, let's see, if you wind it up, the torque that would be causing it to rotate is not in the center, it's where the string is placed. Oh shoot, where the markers go. So there's a torque upward here that is causing it to rotate this way. Okay, I'm just gonna like hammer out some equations really quick. So, let's see. The torque is equal to the force times the radius. This force being the tension of the string. So the torque is equal to tension of the string times the radius it is away from the center. If we have the net force on the yo-yo is equal to its acceleration downward from gravity minus its minus its tension. Then you can solve for tension, so you have tension equals mass times acceleration. Or no, mass times gravity minus its acceleration. So then I can plug that into a few other things. So we also know that torque equals rotational inertia times angular acceleration. So we can set those two things equal to each other. Then you have force times radius equals moment of inertia times angular acceleration. And then if we substitute a few things, this is the tension, so that's equal to mg minus ma times the radius. And then this is equal to 1/2 mr squared times a over r. Now we can cancel a few things. So one of these r's cancels. So we get 1/2 mr a. And then all of the m's cancel. So you get g minus a times r equals 1/2 ra. Those r's cancel, so then you have g minus a. Oh my goodness, I probably screwed this up.
That's an alpha on the side.
This is?
Yeah, it looks like.
No, this is supposed to be an a. Let me see if my math worked out right. 1/2 a. So if you add the, no, this is right. Add the a's to one side, then you get g equals 3/2 a. So then a equals 2/3 g. And I'm not going to do it because it would take too much time, but basically if you plug in the 2m instead of the 1m, you figure out that the tangential acceleration of the yo-yo afterwards is still equal to 2/3 g. So, I mean, it's kind of like a basic concept, but basically we know that the acceleration is independent of the mass of the yo-yo. Oh, goodness.
Just erase it. Yeah.
So,
No, just go around in a circle and then hit the center.
So then, okay, I calculated my error, assuming that if we know that, sorry, I'm running out, I'm over the time. If the tangential velocity should be the same because it undergoes the same acceleration downward. I did my error based on the tangential velocity of the yo-yo on the first trial. So this is just the added mass total, and then the accepted value was the tangential velocity of the first trial. And so then some of my error was kind of high and some was low. Yeah, my hypothesis was not right. And basically I figured out as the mass of a spinning yo-yo increases, the rotational period remains constant and the elapsed spin time in theory should increase. And I also learned through my experiment that based on where I place the mass on here, if it was off by even like a fraction of a centimeter, it really heavily affected the stability of the endo. Yeah, sorry. I would talk about it a little bit more, but I'm not time.